Chapter 5 of Dynamic Thought, or the Law of Vibrant Energy. The Story of Substance. As we stated in a former chapter, there are two aspects of all things, viz. 1. Substance, 2. Mind. In this and the following two chapters we shall consider the first one, substance, which science calls matter. Perhaps it would be as well to begin by asking ourselves the question, what is substance? The answer seems to be anything that takes up room, the body aspect of things, matter occupying space, etc. Some writers have spoken of substance as something tangible that can be felt, but this definition will not do, for there are forms of substance too fine to be felt, and so perhaps the definition, the body of things, is as good a definition as any, taken in connection with the thought that it takes up room. Science divides substance, which it calls matter, into four general classes, viz. 1. Solid matter, which is substance, the parts of which closely adhere and resist impression, such as stone, wood, flesh, etc., the degrees of solidity varying greatly, and sometimes shading into the next class, which is called 2. Liquid matter, which may be described as substance, the parts of which have a free motion among themselves and easily yield to impression, such as water, molasses, etc. The degree of fluidity ranging from some liquids that flow very slowly, such as hot pitch, up to others that flow very freely, such as water, wine, etc. The property of fluidity being also shared by the next higher class, which is called 3. Aeriform matter, which is substance in the form of elastic fluid such as air, gas, vapor, etc., and radiant matter, which is of recent recognition and which is an ultra-gaseous form of substance utterly unlike anything ever before known, consisting of the tiniest particles of corpuscles of substance finer and more subtle than the rarest form of atomic substance known to science. The three classes are well represented by 1. Earth, solid, 2. Water, liquid, 3. Air, aeriform, 4. The corpuscles or electrons or particles of electrified substance, first noticed in connection with the X-rays, radium, etc. But it must be remembered that these four classes of substance are not fixed or permanent. On the contrary, they are changeable either under pressure when subjected to heat or under the influence of electricity, etc. In fact, the word condition is more applicable than the term class. The condition or class of a particle of substance may be changed into another class or condition by the application of the agencies above named. The same substance may exist in 2 or 3 classes under different circumstances. Solids may be changed into liquids and liquids into gases, and vice versa. Metals may be melted, then changed into gas, according to the degree of heat applied. Liquids may be changed into vapor by the application of heat, or into solids by the withdrawal of heat. For an example, we may turn to water, which is a solid in the condition of ice, a liquid in the condition of water, and steam in the condition of vapor. Quicksilver is a metal which is in a liquid condition in our ordinary temperature, but which becomes a solid when subjected to a very low degree of temperature, and may be transformed into a gas under a high degree of heat. Air is a vapor in our ordinary temperature, but has been transformed into liquid air under tremendous pressure, which produced a very low degree of temperature, and theoretically it may be transformed into a solid under a sufficiently low degree of temperature, although so far science has not been able to produce a degree of cold sufficient to freeze the liquid air. It is all a matter of freeze, melt, and evaporate in all forms of substance, and any substance, at least theoretically, is capable of being subjected to any of the 3 conditions just named, and being manifested in the respective conditions of solid, liquid, and aeriform. This may actually be accomplished with the majority of substances at this time, although in some instances we are not able to produce a sufficiently high temperature to melt and evaporate certain solid substances, on the one hand, or a sufficiently low degree of temperature to liquefy or freeze solid certain vapors. But the intense heat of the center of the earth is able to melt rocks and show them as liquid lava flowing from volcanoes. And science teaches that the solid substance of the earth and other planets, suns, etc., existed in the shape of a vapor at one time, and would again take on that condition in case of a collision with another great body, which convert motion into intense heat that would first melt and then vaporize every solid particle of which the earth is composed. If the sun's heat were completely to die out, the cold would be so intense that the air around the earth and all the gases and vapors would be frozen to solids. In physics, the term gas is generally applied to a substance that is aeriform in ordinary temperature, but which may be liquefied in a low temperature. The term vapor being generally applied to the aeriform condition of substances that are solid or liquid in our ordinary temperatures, but which may be evaporated by heat and thus transformed into an aeriform condition, resuming their original form upon cooling. These terms, however, are technical, and practically there is no difference between a gas and a vapor. In the above statements regarding the possibility of the transformation of each of the several forms of substance into other forms, the reference has been applied only to the three better forms, i.e., solid, liquid, and aeriform. The fourth form or state of substance, known as radiant matter, is of too recent discovery to admit of its properties being accurately observed. The best and latest opinion of science, however, is that it constitutes what may be called primal matter, that is, substance from which all other forms, states, kinds, and varieties of substance arise, the stuff from which they are manufactured. Science seems to be discarding the ether theory of the origin of matter in favor of this primal matter. Physical science divides substance into masses, molecules, and atoms. That is, the old physical science did. But the later investigators now see that even the atom may be subdivided. But the old terms may as well be used, at least for the time being. Let us consider these divisions. A mass is a quantity of substance considered as a whole, but which is composed of a collection or combination of parts, molecules. A lump of coal, a piece of iron, a portion of meat, even a drop of water, is a mass. The only requisite for a mass is that it contains two or more parts or molecules. Therefore, a mass is a collection or combination of two or more molecules considered as a whole. A molecule is the physical unit of substance, or, in other words, the smallest part of any kind of substance that can exist by itself and still remain that particular kind of substance, but not the smallest chemical part. The latter is called an atom, and atoms combine to form a molecule. The molecule exists as a unit and cannot be split or separated by physical means, although it may be separated into atoms by chemical means. In order that we may form a clear idea of the molecule, let us take a very small mass of matter. A drop of water, for instance. This drop of water is a mass composed of a great number of molecules. It may be divided and subdivided into smaller and still smaller parts. This division may be carried on until it reaches a point where our sight and instruments are unable to make a further subdivision. But theoretically, the work may be carried on still further until at last a limit is reached where we are unable to divide the water into any smaller parts, without separating its chemical constituents from each other, in which latter case there would be no water at all, its chemical constituents, or atoms, having separated and now appearing as two atoms of hydrogen and one atom of oxygen, separated and apart and no longer forming a molecule of water. Well, this smallest possible part of water, or any other form of substance, is a molecule. Remember, the molecule is the smallest part of that kind of substance that can be produced by division and subdivision without destroying the kind of the substance. It is the smallest part of any kind of substance that can exist by itself and maintain its kind. In order that you may grasp the minuteness of the molecule, we may mention that science claims that no molecule, even the largest, is of sufficient magnitude to be seen under even the strongest microscope. It has been calculated that if a drop of water as large as a pea were magnified to the size of the Earth, the molecules would then appear no larger than the original drop. The space between the molecules is believed to be considerably larger than the molecules themselves. The figures that are necessary to use in connection with molecular substance are likely to stagger the imagination. Besides speaking of the molecules of inorganic substance, it may be interesting to note that a spider's thread is so fine that a piece of it large enough to circle the Earth would weigh only half a pound. And yet each thread is composed of 6,000 filaments. And each of these minute filaments may be divided into tiny bits, and each bit will still be a mass of substance containing thousands of molecules and their constituent chemical atoms. There are living, microscopic creatures so small that 5 millions of them might be crowded into a space the size of a pinhead. And yet each of them have organs, and in these organs fluids circulate. Try to figure out the size of the molecules of the fluids circulating in these tiny organs, not to speak of the chemical atoms. When you handle a coin, an infinitesimal portion of it is worn off. Can you figure the size of the molecules composing that part? When a rose throws off its perfume, it emanates tiny particles of itself. Can you measure or weigh the molecules composing that odor? The human mind is compelled to realize the finiteness when it considers these things. But we have only just begun to consider the smallness of things. An atom is the chemical unit of substance, that is, the smallest chemical part that can enter into combination. It has been considered indivisible, that is, incapable of further subdivision. That is, it has been so considered until very recently, but the latest discoveries have exploded this idea and have shown the atom is composed of certain other things, as we shall see a little later on. Still, we may use the atom as a very good unit of measure, for it still represents the unit of chemical substance, just as the molecule is the unit of physical substance. In order that you may understand the difference between molecules and atoms, physical units and chemical units, let us give you a few examples. Take a molecule of water, the physical unit, you remember. When it is chemically separated or analyzed, it is found to contain 2 atoms of hydrogen and 1 atom of oxygen, both chemical units, remember, which when united and combined form water, but which when separated are simple atoms of certain chemical gases. The proportion in water is always the same, 2 of hydrogen and 1 of oxygen. This is the only partnership that will form water. The molecule of table salt contains 1 atom of sodium and 1 of chlorine. The molecule of air contains 5 chemical gases, of which nitrogen and oxygen are the principal ones, the proportion being about 3 parts of nitrogen to 1 of oxygen. Some molecules are far more complex. For instance, the molecule of sugar is composed of 45 chemical atoms, and sulfuric acid of 7. An atom is estimated at 1/250 millionth of an inch in diameter. But this is not all. The old theory of the finality and ultimateness of the atom has been shattered by the recent discoveries of science. The atom of hydrogen was formerly considered to be the refinement of substance, the ultimate atom, the smallest and finest atom possible or known, the last thing that could be imagined about substance. Some even went so far as to declare that the atom of hydrogen was the ultimate element. That is, the element out of which all other atoms were made, the mother of atoms. It was supposed that all other atoms of matter were composed of a varying number of hydrogen atoms, which themselves were vortex rings in the ether, and that analysis could go no further. Science rested on its oars and pronounced the work of a century completed. But alas, no sooner was the position reached than the discovery of radiant matter and the formulation of the corpuscle theory brought down the whole theoretical structure, and science was compelled to take up the hunt again, and to probe further into the inner recesses of things for the ultimate thing. But nevertheless, atoms still exist, although their finality is no longer urged. The facts remain, although the theory has fallen. Let us see about this latest theory, the corpuscle or electron theory. The discovery of radiant matter and the investigation of the late discovery of radium has led to the further discovery that each atom, instead of being a thing in itself, is a little mass containing numerous other things called corpuscles, or electrons, because electrified. The theory is this, briefly, that each atom is a minute mass of substance containing a number of electrified particles which are known as electrons, in constant motion and vibration, revolving around each other as do the planets, suns, and moons of the universe. In fact, each chemical atom is like unto a universe in itself. The simplest atom, that which was supposed to be the ultimate atom, the atom of hydrogen, is supposed to contain within its tiny self no less than 1,000 minute corpuscles, which because electrified are called electron, revolving and fixed in regular orbits within the containing globe of the atom. The more complex forms of atoms are supposed to contain a far greater number of electrons, the authorities estimating those in an atom of oxygen at 10,000, those in an atom of gold 100,000, and those in an atom of radium 150,000. These figures are of course mere scientific guesses, but when compared with the similar guess regarding the size of the atom, they give a startling illustration of the size of the newly discovered corpuscle or electron. Another authority for an illustration asks us to consider a great globe about 100 feet in diameter, that is, of course, 100 feet through its center. Let the globe represent the atom. Then imagine 1,000 minute specks, each the size of a pinpoint, composed of substance, and each containing, as in a capsule, an atom of electricity. Each speck is revolving around each other in a regular orbit in the great 100 feet through globe, and keeping well away from one another. That will give you an idea of the relative size of the electrons and atoms, and the room that the former have to move about in. Good many feet between each, you will notice. Lots of room and plenty to spare. Try to figure out the size of an electron. Many readers of the magazines have been confused as to the relation between the corpuscles and the electrons, or ions as some have called the latter. The matter is very simple. They are both the same. The corpuscle is the tiny particle of matter, which because it is electrified and has thus become the unit of electricity, is called an electron. From the viewpoint of substance, we call the tiny particle a corpuscle. From the viewpoint of electricity, we call it an electron. These electrons are the tiny particles that pour forth from the pole in the Crookes tube and constitute what are known as X-rays, cathode rays, Becquerel rays, etc. They also are the particles that are thrown off and emitted by radium and similar substances. They exist in the atom, as explained, but also are found free and independent, and in the last condition or state are thrown off in the aforesaid rays and by radium, etc. So far, the corpuscles are known only as charged with electricity, and the electron only as a tiny charge of electricity with which the corpuscle is charged. But science dreams of corpuscles of substance other than electrons, in which case the old occult teachings of light dust and heat dust, etc., will be verified. The electron contains a powerful charge of electricity, as much in fact as an atom 1,000 to 150,000 times its size will carry. But science is wondering how these highly charged particles manage to hold together in the atom, so rigidly coherent as to appear indestructible. We think that we may get a hint at the matter a little later on in this book. Science, or at least some scientists, are wondering whether the whirl or vibration of the corpuscle might not produce that which we call electricity, and whether, when the motion is intensified, waves of electricity will not be emitted. The writer fully agrees with the idea and finds that it fits closely his own theories regarding substance and motion. But the reader is cautioned against falling into the error of many recent popular writers on the subject, some of whom have used terms calculated to convey the idea that the corpuscle, electron, is electricity itself, rather than tiny particles of substance called corpuscles, charged with the unitary charge of electricity and therefore called electrons. But for that matter, electricity is only known to us as associated with some form of substance, and not as a thing in itself. We shall see the reason for this as we proceed with this book. These corpuscles are destined to play a most important part in the theories of science from now on. They already have overturned several very carefully and laboriously erected theoretical structures, and many more will follow. Among the many important ones evidently doomed to the dust heap being the vortex ring atom theory, and other theories built upon the etheric origin of matter, and other theories concerning the ether, even to the extent of breaking down the theory of the ether itself, which theory had almost come to be considered a law. We shall further consider the corpuscles and their qualities, characteristics, etc. in the next chapter, for they have an important bearing upon the theories advanced in the course of the study of this book. End of Chapter 5. Chapter 6 of Dynamic Thought, or the Law of Vibrant Energy, by William Walker Atkinson. Substance and Beyond. Science has ascribed to substance certain characteristic qualities which it calls properties. It divides these properties into two classes, viz. 1. Molecular properties, sometimes called physical properties, and 2. Atomic properties, sometimes called chemical properties. Molecular properties are those which may be manifested by substance without disturbing the molecules, and consequently without affecting the kind of substance. Atomic properties are those which concern the atoms when free from molecular combination, and which consequently cannot be manifested without changing the kind of substance. Science before long is likely to add a third class of properties, namely corpuscular properties, relating to the corpuscles or particles of radiant matter, but so far it has not had the opportunity to sufficiently observe these qualities, except in a general way. There are certain general properties that seem possessed by both mass, molecules, and atoms, and probably by corpuscles. These general properties are as follows. Shape, that property whereby substance takes up room. This property manifests in three directions, called dimensions of space, namely, length, breadth, and thickness. Weight, that property whereby substance responds to gravity. Weight is simply the measure of the attraction. Impenetrability, that property whereby two bodies of substance are prevented from occupying the same space at the same time. A nail driven into a piece of wood simply pushes aside the molecules and occupies the space between them. Substance is never actually invaded or its actual territory occupied by other substance. Indestructibility, that property whereby substance is prevented from being destroyed or annihilated. Although the forms of substance may be changed or transformed into other forms, still, substance in itself is not destroyed, and cannot be under the existing laws of the universe. Mobility, that property whereby substance responds to imparted motion. We shall notice this property in our consideration of motion. In addition to the motion of the mass and the movements of molecules and atoms in response to its attraction, there is another form of motion constantly going on, without reference to the attraction or impressed motion of the mass. The molecules of all bodies are always in a state of rapid motion, called vibration. In solids this vibration is short, being restrained by the close cohesive position of the molecules. But in liquids, the molecules being further separated, the vibration is far more rapid, and they move around and slide over each other with comparatively little resistance. In gases and vapors the molecules have a splendid field for motion, and consequently vibrate in wide fields and orbits, and dash around with the greatest velocity. The atoms also are believed to vibrate rapidly in accordance with their own laws of vibration, and the corpuscles are believed to far excel the last two mentioned particles in intensity, rapidity, and complexity of their vibrations, as we shall see a little later on in the book. All substance is in constant motion and vibration. There is no rest in substance. Inertia. That property whereby substance may not move unless in response to imparted motion, nor terminate its motion when it is once imparted, except in response to some other manifestation of impressed force. Science holds that this impressed force or imparted motion must come from without, but the writer holds that force may also be expressed from within, as may be seen by reference to subsequent chapters of this book. Attraction. That property whereby particles or bodies of substance 1. Draw other particles or bodies toward themselves, or 2. Move toward other particles or bodies, or 3. Are mutually drawn together. This property manifests in 4 forms, generally referred to as separate and distinct from each other, but which the writer believes to be but forms of the same attractive power, and which he believes to be a mental process, at the last analysis, a revolutionary claim which will be supported by argument in later chapters of the book. These 3 forms of attraction are known as 1. Gravitation, 2. Cohesion, 3. Adhesion, and 4. Chemical affinity, or chemism. We are invited to consider them briefly at this point, further investigation being reserved for our chapters on motion and dynamic thought. Gravitation. This term is usually applied to the attraction between masses of substance, such as the sun, the earth, and masses of substance on or about the earth's surface. However, Newton, who discovered the facts of gravitation, states the law as every particle of matter in the universe attracts every other particle, etc. Cohesion. This term is used to indicate the attraction between molecules by which they are combined into masses or bodies. Cohesion causes the molecules to unite and cling together, thus forming the mass. Adhesion. This term is used to indicate the attraction between masses which causes them to stick together, without a cohesion of their molecules. Adhesion operates through the adjacent surfaces of the 2 masses. It may be considered as a lesser form of cohesion. Chemical affinity, sometimes called chemism or atomic attraction. This term is used to indicate the attraction between the atoms, by which they combine, unite, and cling together, forming the molecule. Science has before it the task of naming and classifying the attraction between the corpuscles, by which they combine and form the atom. But whatever the name, it will be seen that it represents but another manifestation of attraction. Arising from molecular attraction or cohesion are several properties peculiar to masses having molecules, and resulting from the tendency of the latter to resist separation. We had better consider them briefly, in order to understand the power of molecular attraction and its incidence. Porosity. This property indicating the distances observed by the molecules in their relation to each other, which varies in different kinds of substance. All substance is more or less porous, that is, has more or less space existing between the molecules. The degree depends upon the closeness. Compressibility and expansibility, sometimes mentioned as properties, are but results of porosity. Elasticity. That property whereby bodies resume their original size and form after having been compressed, expanded, or bent. The result is caused by the inclination of the molecules to resume their original positions. What is sometimes called plasticity is merely the reverse of elasticity, and denotes a limited degree of the latter. Hardness. That condition resulting from molecular attraction resisting the forcible entrance and passage of other substance between the molecules. Tenacity. That condition resulting from molecular attraction resisting the forcible pulling asunder or tearing apart of the mass. This condition sometimes is called toughness. Malleability. That condition resulting from molecular attraction resisting the forcible separation of the mass by pounding, hammering, or pressure. The resistance is passive, and consists of the molecules allowing themselves to assume a spread-out formation rather than to be forced apart. Ductility. That condition resulting from molecular attraction resisting the forcible separation of the mass by a drawing out process. The resistance is passive, and consists of the molecules allowing themselves to be drawn out into a formation of the shape of wire or thread, rather than to be pulled apart. In any of the above cases we may intelligently and with propriety substitute the words molecules by means of cohesion, resisting, etc., for the terms above used, molecular attraction, resisting, etc. All masses of Substance, probably molecules as well, are capable of expansion and contraction, both phenomena in fact and in degree resulting from the relation of the molecules. Contraction is a crowding together of the molecules; expansion, a getting apart of them. Density, the amount of Substance in relation to a given bulk. Volume, the size or bulk of a body of Substance. Mass, besides being used to designate a body of Substance composed of two or more molecules, the term mass is used to designate the total quantity of Substance in a body. An application of the above terms may be seen in the following illustration. A quart of water occupies a certain space, and has a certain volume, mass, and density. Convert the same mass of water into steam and it expands to a volume of 1,700 times that of water, but as no molecules have been added the mass remains the same. But as a quart of steam weighs 1,700 times less than the same volume of water, the density of steam is 1,700 times less than that of water. As the volume of a given mass increases, the density decreases in the same proportion, but the mass remains the same. Mass therefore has two factors, i.e., volume and density. The density of a mass is determined by the weight of a certain volume of it. The above consideration of the properties of Substance dealt only with the molecular properties or physical properties, as they are sometimes called, that is, with properties depending upon the existence of the molecules. When we consider the molecules as being composed of atoms, and when we consider the processes whereby these molecules are built up of, or broken down through the separation of atoms, we come to the subject of atomic properties, or chemical properties, as they are often called. The atomic properties of Substance consist principally in the power and manifestation of motion, in the direction of combination, separation, and the complex motions resulting from the same. This motion is manifested by reason of atomic attraction, sometimes called chemical affinity, which we shall consider a little later on in this chapter. Atomic principles, as above mentioned, are best illustrated by a reference to chemical changes, and we shall now examine the same. And the better way to consider chemical changes is by comparing them with physical changes, or changes of the molecules. Some physical changes in Substance are brought about by heat, which tends to separate the molecules, or rather to allow them to spread out away from each other, so long as the high temperature is maintained, the degree of their nearness being influenced by temperature. Other physical changes are produced by outside forces, separating the molecules to such an extent, to such a distance, that their cohesive force is lost, and the solid matter is said to be broken, or even reduced to dust. Other physical changes are brought about by electricity, causing the molecules to separate and disintegrate. Chemical changes, as distinguished from physical changes, do not involve or deal with molecules, the action being solely upon the atoms of which the molecules are composed. Physical changes separate molecules from each other, while chemical changes destroy and break up the molecule, so that its identity is forever lost, its atoms therefore either existing free-form combinations, or else recombining with other atoms and forming new combinations. Chemical changes are occasioned by either physical or chemical agencies. The physical agencies generally employed are heat, electricity, light, pressure, percussion, etc. The principle of chemical changes is that the atoms are possessed of and subject to what is called atomic attraction, or chemical affinity, which may be defined as an attraction or love existing in varying degrees between atoms. This affinity causes atoms of one element to seek out and ally themselves to atoms of another element, the element of choice or preference being strikingly in evidence. Atoms of different elements form marriages and cling together in harmony until perchance by some physical or chemical agency The molecule is brought in sufficiently close connection with another molecule composed of different elemental atoms, when, alas, one of the atoms of our molecule finds that it has a greater affinity for some other elemental atom in the second molecule, and lo, it flies away, leaving its first partner and seeking the new charmer. Divorce and remarriage is a common thing in the world of atoms. In fact, chemistry is based upon these qualities. Physical and chemical changes gradually transform solid rock to earth or soil. Disintegration, by the action of changes in temperature, rains, and atmospheric influences, and other physical changes, have slowly worn down the rocks into dirt, gravel, clay, loam, etc., and decomposition by chemical change that set the atoms free from their combination has aided in the work. There is no rest in the world of Substance. Everything is changing, constantly changing. Old forms give way to new, and these, grown old while being born, are in turn replaced by still newer, and on endlessly. Nothing persists but change, and yet nothing is destroyed, although countless forms and shapes have succeeded each other. Substance is always there, undisturbed and unaffected by the varieties of forms it is compelled to undergo. Masses may change, and do change. Molecules may change, and do change. Disintegration and decomposition affect both, and bring to them the death of form. But their substance endures in the atom. Atoms may change and decompose, or undergo whatever change that is their fate, and still the corpuscles, or what lies beyond the corpuscles, will remain. The atom was once regarded as eternal, but now even it seems to be capable of dissolving into some finer division of substance, and perhaps still finer subdivisions await it. That familiar form of substance that we call earth, dirt, soil, etc., is but the result of disintegrated rock, which has crumbled and lost its former form through the action of air, water, and atmospheric influences. And the rocks themselves, from which the soil came, were at one time a sea of melted, flowing liquid substance, somewhat resembling volcanic lava, and this melted rock is thought to have been condensed from the same principles in the shape of vapor that existed in the early days of our planetary system. Vapor, gas, liquid, semi-liquid, solid rock, soil, the substance unchanged, the forms totally unlike. Helmholtz estimates the density of the nebulous vapors of Substance as being so rare that it would take several millions of cubic miles of it to weigh a single grain. Oh, Nature, what a wizard thou art! We have spoken of air and water in a former chapter, and their constituent atoms have been named. And from these three great reservoirs of Substance, the earth, the air, and the water, are obtained all the material that goes to form the bodies of the animal and vegetable kingdoms. The plant draws its nourishment from the soil, the air, and water, and in its wonderful chemical laboratory is able to transform the elements so drawn from these sources into a substance called plasm, which consists principally of carbon, oxygen, nitrogen, and hydrogen, being nearly identical in composition to the white of an egg, and which constitutes the basis of animal and plant bodily structures. All the material of the physical bodies of men, animals, and plants are but forms of plasm. The animals and man obtain their nourishment directly or indirectly from the plant body, and so at the last we are seen to draw from the soil, air, and water all our bodily nourishment, which we convert into bodily structure, bone, muscle, flesh, blood, veins, tissues, cells, etc. And the chemical atoms of our bodies are identical with those in the rock, the air, the water. And so you see the universality of Substance and its countless forms and appearances. Chemistry resolves Substance back into about 75 simple substances, of which atoms are the units, which simple substances are called elements. From these elements, by their atoms, all other substances are formed by combinations, the number of such possible combinations being infinite. An element, in order to be an element, must be a simple substance, that is, must be incapable of further analysis into some other elements. The 75 elements now recognized by science have never been resolved into other elements by chemical analysis, and therefore are accepted as simple. But it is true that other substances that were formerly considered as simple elements were afterward decomposed by electricity and found to consist of two or more simpler substances, or elements. Thus new elements were discovered and old ones discarded as not elemental. And this fate may be in store for a number of the elements now on the list, and many new ones may be discovered. For a long time science was endeavoring to trace all elements back to hydrogen, the latter being considered the ultimate element, and its atoms composing all the other atoms under varying conditions, etc. But this theory is now almost abandoned, and science rests on its list of 75 elements, the atoms of which are composed of electrons. Some have hazarded the theory that the elements were all forms of ether. See next chapter. Their apparent differences resulting merely from the varying rate of vibration, etc. And in fact, such theory was about finally adopted as a working hypothesis until the discovery of the corpuscle. Everything in substance now seems to be moving back to the corpuscle, as we shall see a little further on. The following is a list of the principal elements known to science today: aluminum, antimony, arsenic, barium, bismuth, boron, bromine, cadmium, calcium, carbon, chlorine, chromium, cobalt, copper, fluorine, gold, hydrogen, iodine, iron, lead, magnesium, manganese, mercury, nickel, nitrogen, oxygen, phosphorus, platinum, potassium, radium, silicon, silver, sodium, strontium, sulfur, tin, zinc. Of the above, hydrogen is by far the lightest in weight. In fact, it is used as a unit of atomic weight, its weight being marked 1 on the scale, gold 197, lead 207, silver 108, oxygen 16, nitrogen 14, iron 56. The discovery of the corpuscle or electron rudely shattered the vortex ring theory of the origin of the atom, and now, instead of the atom being regarded as a vortex ring in that hypothetical, paradoxical absurdity, the ether, it is believed to be composed of a vast number of tiny particles called corpuscles, as we saw stated in our last chapter. These corpuscles seem to be the last thing in substance, its last known state of refinement, and already it is being proclaimed as the last sought for primal matter or ultimate substance. Whether or not a still finer state of substance will be discovered, science is unable to say, but thinks it unlikely. But we must not overlook the old occult teaching indicating a state of substance so fine that it is imperceptible and only recognizable as apparently free force, its covering or vehicle of substance not being evident. This would seem to indicate a still further refinement of substance, although perhaps the corpuscle or electron will answer to fill the bill in the case. As to the corpuscle being primal substance, it must be admitted that its advocates have presented a very strong case. One of their most important points is that although molecules differ very materially from each other according to their kinds, and while atoms likewise manifest very plainly their kind, the corpuscle seems to possess only one kind, no matter from what form or kind of substance it is thrown off. Just think what this means. It means that the finest particles of gold, silver, iron, hydrogen, oxygen, and all the rest of the elements are composed of identically the same material, and exhibit no differences in kind. The elements are no longer simple, all substance is one, at the last analysis. The corpuscles seem to possess the same mass, to carry the same charge of electricity, to act precisely the same, irrespective of their source. No difference in size, mass, or character, as in the case of the atom. All are identical, save in the rate of their vibration at the time of observation, which is simply a matter of more or less motion. Space seems to be flooded with these tiny particles, these units of substance. They stream from the sun, the stars, and every body highly heated. Likewise, they stream from the bodies of highly electrified substance. Groups of these corpuscles, absolutely identical in nature, size, mass, etc., constitute the atoms of the 75 elements, the kind of element seemingly being dependent upon the number and arrangement of the corpuscles and possibly their rate of vibration. Every atom is like a great beehive with a swarm of corpuscles vibrating, moving around each other, and upon their own centers. And if by the action of intense heat, transmitted or caused by interrupted motion, or if by a strong electric charge, some of these corpuscles are detached from the atoms, or possibly an atom broken up, they fly off through space at a marvelous speed of many thousand miles an hour. So we see that these wonderful corpuscles look very much like primal matter or ultimate substance, the stuff out of which substance is made. And taking you back to the chapter on the universality of life and mind, the writer would remind you that in their motions and evident attraction, etc., these corpuscles evidence the same life and mind that we observed in the molecules and atoms. It must be so, for what is in the manufactured article must be in the material of which the article is made. And so, even here, life and mind have not escaped us, nor will it in the ether. And speaking of the corpuscles as manufactured articles, we are reminded of Herschel's thought about the atoms, when they were regarded as primal matter and likely to be uniform and, at the end, of one primal substance. Although Herschel's conception does not now apply to the atoms, it may be transferred to the corpuscles. Herschel thought that the fact that the particles of substance were likely to be found to be uniform in size and identical in nature and characteristics indicated that they might be akin to manufactured articles, turned out from the same great machinery of creation. This idea would indicate that the Creator applied the rules of careful manufacture to the manufacture of the particles, the uniformity operating in the direction of 1. Economy of material, 2. Utility through interchangeability, replacing broken or discarded parts, etc., and also 3. Conformity to a standard of size, quality, etc. The thought is interesting, and is mentioned here for that reason. It is not affected by the supposition that there may be a still finer and rarer form of substance from which the particles are manufactured. In fact, the idea of Herschel, if closely analyzed, would seem to indicate some such raw material from which the articles were manufactured. End of Chapter 6.